Alright, chemistry. When last we left, I was trying out this new thing. I'll stick with it for a little bit. I feel like I should give it an old college try. So I should I'll give it like a week, maybe two. Uh, just to, again, see how I feel about it versus whiteboard. If you have strong preferences one way or the other, let me know. Send me an email. Otherwise, the last time we left off was before the lab, right? So fully remote students, y'all should have seen a lab video go up about the flame test, right? It was difficult to film that because I had to make sure not to spray the computer. Anyway, but new notes going up, right? We left off here talking about valence electrons, this outermost shell. I realize it's a little hard for you to see my cursor now. Maybe that's an interesting point to bring up. But talking about the valence electron, which is this outermost electron, or in fluorine's case, there are 7 outermost electrons. And they are interesting because those are the first electrons that actually interact with other atoms. That's kind of really how chemical reactions take place. And then I said we're going to skip this, and we're going to skip this, and we're going to skip this. I will come back to these questions as we review. So page 67 will come back to it, but right here, oxidation and reduction. All right, this topic can be a bit challenging. Please do your best to stick with me. It will not always be superbly intuitive, but I swear, I will get you through this. There are a few phrases in here that will seem silly, but please do your best to remember them. They will help you get through the questions that are like on this topic, all right? So oxidation and reduction are very specific chemical reactions. They arise out of the competition for electrons, right? Different elements actually want to either keep or lose their electrons more or less than other elements. So the different substances in a chemical reaction, whether that's compounds, elements, or combination of both, they will compete over who gets to keep electrons and who does not. Now here is where the first big what the heck kalimlim moment comes in. A loss of electrons is known as oxidation. A gain of electrons is called reduction. And immediately, why is gaining electrons being reduced? I know. For the sake of what's happening here, gaining electrons is reducing the charge. Right? I know it's not super intuitive because you're physically gaining a thing, but electrons are so small that you're not really gaining mass or gaining size. So what's being reduced is the oxidation number or the charge, right? The charge of that substance is going to be reduced because we're gaining electrons. Anyway, please star this, underline this, do something. Leo says grr, all right? The chemistry cat, all the memes with the cat with the beaker and anyway, it looks dumb. Chemistry cat's name is Leo. That's not official. That's just in Kalimlim's class canon. So that's not a universal truth. But for the sake of argument, chemistry cat's name is Leo, and he says grr because he thinks he's a lot bigger than he actually is. Just run with it. Leo and grr. The reason that comes up, if you lose electrons, it's oxidation. If you gain electrons, it's reduction. That immediately is something to help you remember which goes with which. Leo says grr means that if you lose electrons, it's oxidation. And if you gain electrons, it's reduction. All right? Sometimes the question is as simple as that. Oxidation is a process by which a substance does what? It loses electrons. All right? So, I will most frequently abbreviate this as redox. It's just simpler than saying oxidation reduction, right? So because redox involves electrons, it can help to think of things as just gaining or losing negative ones. If that doesn't help you, don't do it that way. Think of literal electrons. Oxidation and reduction have to occur simultaneously, which means they happen at the same time. Electrons are transferred away from one thing, the one that gets oxidized, to another thing, the thing that gets reduced. And again, this is one of those things that you'll have to try to resolve in your head. Being reduced means that your number goes down. So electrons goes up. Right? Now, these are weird. These are backwards. Right? These two bullet points are backwards. They have the word agent in them. The only time that I really see agent is in spy movies. If you see a double agent, you have to think the opposite, right? Anything that gets oxidized is known as a reducing agent. I know, already just your minds are exploding. It can be confusing, but I swear. Leo says Gur. Agent think opposite. Alright, so if you see what is a reducing agent, okay, agent think opposite, find the thing that gets oxidized. Similarly, anything that gets reduced is called an oxidizing agent. Agent think opposite. Right? I know. It's a lot to take in, right? For one thing. I am only going to do one more thing. I'm going to stick right here on page 68, and there are going to be some example questions to do based purely on these definitions: oxidation, reduction, oxidizing agent, reducing agent, and how can I tell if something is redox? All right, so very quick notes today, because I want to make sure this is clear. I also want to try to get this whole electron section done before the break, because I want to have all of this information done and tied up and neatly finished before the break. I don't want to give you break and give you an opportunity to kind of like forget things. Not that you would ever forget things over a break, right? But just to avoid that potential problem, all right? Leo says Gur. If you lose electrons, it's oxidation. If you gain electrons, it's reduction. They happen at the same time. If you see agent, think opposite. Reducing agent means it gets oxidized. Oxidizing agent means reduced, right? Now, we have looked at chemical equations in the past. Now we can look at them in the context of, is this redox? All right, how do we determine if a reaction is a redox reaction? Step 1 says to review page 23 of the notes. Assign oxidation numbers to every element in the equation. Oxidation numbers are the charge of that thing while it's an ion. And I'll go through, we'll look at the example below. All right. Step 2, any diatomic molecules and single elements that are uncombined, their oxidation state is 0. Okay? So I have to assign oxidation states to everything. If it's a diatomic or it's on its own, it has a state of 0. So I look on the reference table. If it's combined with something, I will look what it says. If it's not combined with something, I will write a 0. Any substance whose oxidation number becomes more positive if it goes up on the product side compared to the reactants has undergone here we go. Oxidation. Right. If the oxidation state, if the number goes up, it's going through oxidation. Any substance whose oxidation number becomes more negative on the product side, so the number goes down. The number goes down. The number goes down, that means reduction. Yes, I said the number goes down several times there. I'm sorry, I can't help it. An equation has to have both of them to be considered redox. Alternatively, here's a side note. All single replacement reactions are redox reactions. So just for reference, all right? Now, the example that we have here, which I will zoom in on, is the following reaction a redox reaction? Or maybe I won't zoom in on? No, we'll zoom in. Okay. So is this redox? Right? Rule number 1, assign oxidation numbers to everything. If it's a diatomic or a single element, it has an oxidation state of 0. Okay. So assign oxidation states. This copper gets a 0. This silver gets a 0. I'll always do the easy ones first, right? And if you look, there they are, right? Here's the thing that happens. Ag on this side, on the left side, it's combined with stuff. It has a charge. Unbelievable. Yep, that's my desktop background. That's real life. One take, kids. One take. Alright. That was weird. Hello? There we go. The silver, right here, has a charge of +1. And the reason for that is if I look at silver, its charge here in the top corner is +1. I know it's a smidge hard to read, but there it is. +1 in that top corner. So, Ag has a charge of +1. Now, if you look, this section here, NO3, I've labeled it as all one thing. It has a giant charge of -1. NO3, apparently I have to scroll. I can't use my click wheel. That's fine. Is a polyatomic ion. NO3 is nitrate, and this whole thing has a giant charge of -1. So I can use that to my advantage here. The reason I can use that to my advantage, if you look, NO3 is on this side, and NO3 is on this side. So this whole thing has a charge of -1, this whole thing has a charge of -1. Copper is here with a -1, right? It's here with a -1, but there are two of them. So that's -2 total. Means that the copper has to be +2, right? So if we look at step 2, right, copper 0 turns into copper +2. So copper was oxidized. This silver, though with a +1, turns into silver with a charge of 0. It was reduced. We have oxidation, we also have reduction. This is redox. The electrons are transferred from copper, it loses electrons, and silver gains them. Right? Alternatively, look at the form of this reaction. That reaction is a single replacement reaction. That's the first thing to look for. That's the easiest version. Is this a redox reaction? Yeah, it's single replacement. It has to be redox. Technically, realistically, I could have stopped once I found copper had a charge of 0 when it's on its own. Silver had a charge of 0 when it was on its own. Right here, when I labeled this silver with a +1 charge, I know that silver changes charge from one side to the other. That automatically makes it redox. Something changes charge from the reactant side to the product side. Right? Now, I'm going to throw up some questions. They're going to be in the Orange Book, which, I don't know, maybe you've forgotten we have it. We haven't used the Orange Review Book for a bit. There are going to be some Orange Book questions on redox definitions and on identifying redox reactions. Right? Possibly on, like, identifying what is oxidized or what is reduced, like this little section here. But it'll be just on this, right? Homework is just, please do the homework. I will go over it first thing tomorrow before I get into what we call half reactions. Right. I will tell you that after this redox section, things get much nicer. Things roll along much more easily. Until then, stick with me. I swear that I will get you through this. All right? Leo says Gur. If you see agent, think opposite. In order to figure out if something is redox, see if it's single replacement. If you can't tell based on that, start labeling oxidation states. If something changes oxidation states from one side to the other, you have a redox. If not, you have a boring reaction. All right? Look for the review book questions. I will see y'all next class or next video. In the meantime, take care of yourselves, kids. Be good.